Hi, my name is Nick Weinhold, and in this video I will talk about the 8 fallacies of distributed computing. These are 8 statements that developers or architects, particularly those that are new to designing and implementing distributed systems, believe are true. By believing these statements to be true, we often design systems that are unreliable and lead to pain points in the future. In this video, I will outline the 8 fallacies and describe methods to avoid them. By avoiding these fallacies, we can develop systems that are robust and dependable. Just a quick introduction before I delve into the 8 fallacies. Let's just start with a definition. A fallacy is a mistaken belief. It's an idea or belief that is misleading or false. In the case of distributed systems, these are misconceptions that we may have when designing or implementing the system. Assuming these statements to be true can result in issues in the future. It can impact reliability, resilience, or security. When designing a distributed system, we should prepare for the worst case scenarios. The fallacies aren't saying that the network is always unreliable or that the network is always insecure, etc. Instead, that sometimes one or more of them will be unreliable, and therefore we should design our system accordingly. Avoiding the fallacies will enable us to engineer robust and dependable systems. The origin of these fallacies is unclear. It is generally accepted that they originated at Sun Microsystems in the early 1990s, and they are usually credited to L. Peter Deutsch. However, it appears that the first 4 are from Bill Joy and Tom Lyon, fallacies 5, 6 and 7 are from L. Peter Deutsch, and the 8th fallacy comes from James Gosling, the lead designer of Java. As an overview, here are the 8 fallacies. Number 1, the network is reliable. Number 2, latency is 0. Number 3, bandwidth is infinite. Number 4, the network is secure. Number 5, topology doesn't change. Number 6, there is one administrator. Number 7, transport cost is 0. And number 8, the network is homogeneous. Let's now take a look at each one in more detail. The first fallacy is that the network is reliable. In reality, we can't trust the network. It is possible that some hardware has failed, the power has gone out, there is some misconfiguration, or maybe we're under a denial of service attack, and so on. If the code is written under the assumption that the network is reliable, in the future, when the network becomes unreliable, we can quickly realize that our initial assumption is incorrect and that our system is adversely impacted. We need to design the system to take this unreliability into account. We must have the mindset where we view failures as routine and expected rather than an exceptional event. How can we do this? We need to engineer our system so that we have redundancy in place so that we can mitigate these failures. We need to consider our particular use case. For example, we may make a request to charge a customer. It's possible that we get an HTTP timeout exception, but we don't know if the server processed the request. By retrying the request, we could end up charging the customer twice. We therefore need to think about making the requests idempotent. In other words, issuing the same request several times will result in the customer only being charged once. We can make use of messaging services such as RabbitMQ, Azure Service Bus, etc., where the message queues use a pattern known as store and forward, ensuring that the message gets to the right place. This way, we move away from a typical request-response approach to an asynchronous fire and forget approach. These messaging services can provide benefits such as deduplication, transactions, etc., but do require careful thought when thinking about the logical flow of our system. The second fallacy is that latency is 0. Accordingly, we must design and implement our system to take latency into account. When these systems are all within the same node or within a local area network, the latency can be close to 0. However, when running on a wide area network, the latency can quickly increase. Latency is constrained primarily by distance and the speed of light. Even if conditions are perfect elsewhere, network packets won't be able to travel faster than the speed of light. For example, it's about 150 milliseconds for a packet round trip between USA and Europe versus 0.5 milliseconds for a round trip within the same data center. Whilst we can't do anything about the speed of light, we can, however, work around the distance by bringing the data closer to the users, for example using CDNs for static content, or if we're using a cloud provider such as Azure or AWS, choose a region carefully so that it is in close proximity to the end users. We can reduce the impact of round trips across the network by making fewer requests, but request all the data that we may need. We can also think about the performance of our servers, for example ensuring that load is evenly distributed and that servers are powerful enough so they are not being bogged down by handling requests. The third fallacy is that bandwidth is infinite. Although bandwidth has increased in the 30 years since the fallacies were first written, we obviously still cannot send infinite amounts of data over a network. Whilst bandwidth has increased, what we wish to do has also increased, for example viewing higher resolution videos, online gaming, etc. But we cannot assume that we don't have a user with limited bandwidth. We need to think about what an appropriate amount of data to transfer is for a given use case. In conclusion, there is somewhat of a conflict between fallacies 2 and 3. To work around fallacy 2, we want to transfer more data in order to reduce the number of round trips over the network. But to work around fallacy 3, we want to minimize the amount of data that is transferred to reduce bandwidth usage. We need to find the correct balance and think about the data that is transferred. The fourth fallacy is that the network is secure. There are many different ways that the system could be compromised: a rogue employee, data that's unencrypted, vulnerabilities in our code, or third-party dependencies, and so on. How can we mitigate this? No network is 100% secure, and as our system is distributed, a network is required for communication. We should take a layered approach to security, or defense in depth. We must have measures in place to provide protection at the different layers: the system level, network level, application level, etc. Each layer should have its own strategy with regards to security, but also have a good understanding of how these strategies will interact with each other in order to have an adequate and comprehensive approach to security. We can use tools such as Sneak to scan our dependencies, or tools such as Veracode to perform static analysis of our code to identify vulnerabilities. Finally, we can also apply threat modeling to identify any areas that may be vulnerable. The fifth fallacy is that topology does not change. In a distributed system, the network structure can change regularly, whether by accident, a server failing for example, or deliberate actions such as adding or removing a server. With tools such as Docker or Kubernetes, or using cloud infrastructure, changes to network topology are even easier to make. Our system should be able to adjust to changes in the network topology whilst remaining available. If a node goes offline for whatever reason, can traffic still flow through the system? No node should be considered as indispensable. We want to get into a mindset where no server is irreplaceable. We want to assume that any server can fail, and we should test those assumptions. There are tools such as Chaos Monkey from Netflix that allow us to test how resilient our systems are when a virtual machine or container is terminated. We should embrace automation. Through infrastructure as code, we can recreate or tear down infrastructure as necessary and create the configuration to locate services quickly. We can also make use of service discovery tools such as Eureka from Netflix. These tools allow services to find and communicate with each other without hard-coding host names or ports, etc. The sixth fallacy is that there is one administrator. A distributed system, particularly in a global organization, will have many system administrators. Communicating or coordinating changes to networks or systems can be complex. In addition, any third-party services we use will have their own system administrators, so we will need to think about how we manage external dependencies. Potentially, we may wish to introduce an abstraction layer to reduce the impact of any third-party outages. We can make use of DevOps or infrastructure as code to simplify the management of configuration or provisioning of new systems, etc. By having this in code, we can avoid undocumented configuration changes. By decoupling our systems, we can deploy or upgrade different parts of the system independently and can ensure that the overall system is resilient. The release process should also be the responsibility of everyone involved, and system administrators should be involved earlier in the process. Are firewalls properly configured in all environments? Is the necessary infrastructure provisioned? Is there an ongoing high-priority incident that may cause the release to be postponed? By having everyone take responsibility, issues can be avoided. We also want to make troubleshooting issues easy. We want to have adequate monitoring and logging in place so that issues can be identified easily. We want to have central logging in place so that we don't need to pull logs down from many different systems to debug an issue. The seventh fallacy is that transport cost is zero. In any computer network, there will be a non-zero cost to transfer data, both in terms of time, which we spoke about in the second fallacy, that latency is zero, and in terms of resources. This fallacy is concerned with the consumption of resources. Any computer network will have upfront and ongoing costs. If we're on-prem, the servers, network switches, load balancers, staff to ensure that the systems are running smoothly, etc., all cost money. Even if we are using a cloud provider such as AWS or Azure, rather than paying up front, we instead lease the resources from them. We also have to pay for the bandwidth used. There is an extra component to the overall cost that can easily be missed, and that is the cost of serializing and deserializing data. This can quickly become relevant in a cloud environment when we may be paying for compute time. We should remember fallacies 2 and 3 and design our system to avoid unnecessary data transfer over the network and attempt to keep these payloads as small as we can. It may be worth considering lightweight formats such as protocol buffers in a performance-critical system. We also need to balance our use of hardware with the cost and ease of development. We need to consider the costs, but also consider that prematurely optimizing may cause more issues than it's worth. We really need to monitor our resource usage to determine whether or not it is an issue. The eighth fallacy is that networks are homogeneous. The reality is our systems will be integrating with many different devices, running different operating systems and different browsers. The various components that make up the distributed system may also be written in different programming languages. We want to design our systems with interoperability in mind. If possible, we want to avoid proprietary protocols and instead make use of open standards that enable interoperability. Good examples would be HTTP, WebSockets, JSON, etc. In conclusion, designing a reliable distributed system is difficult. Even though these fallacies are about 30 years old and technology has improved in that time, for example, networks are more reliable, we have increased bandwidth, etc., these fallacies are still relevant today. If we believe these fallacies and don't design our system accordingly, we can end up with a system that is unreliable and error-prone, making our lives harder in the future. Instead, we want to assume the opposite. We want to design our system for an unreliable network. We want to design our system for a network that is insecure, etc. We want to think about what can go wrong and design our system for those worst case scenarios. This will give us a dependable system. As always, thanks for watching. I hope you found this video to be useful and informative. Please hit the like and subscribe buttons, and I hope to see you in a future video.